let's go ahead and start talking about some of this stuff. So today is going to be kind of short, and not even kind of, it's going to be very short, as a matter of fact, because I don't have a whole lot of new stuff to show you today. We do have a lab that goes kind of along with this stuff that we're seeing today, and that lab's a bit more involved than we normally see them. So I'm cutting this one early so that we've got plenty of time to work on that lab, and I'm not stealing too much time away from you or anything else. So, last time we were starting to look at these things, we were talking about basic components that you would find in circuits, right? We've talked about current, we've talked about resistance, we've talked about potential difference. Now, circuits are how we combine all of those into practical applications that run your everyday life. So today, we're starting to introduce a little bit more funkiness to it, right? A little bit more complexity, some more things that we can do with circuits. We're going to grow on that, what we have seen so far, and start to explore what other things we can start to do. But before that, I would like to talk about some of the stuff from last time, just to hit on this one more time. So remember that when we were talking about solving out any circuit, if we want to solve out a circuit, that means we're describing every potential difference, every current, every resistance, every piece of information that we could possibly have about that circuit. To solve out the circuit is to find all of that information, or be very close to finding it, right? If we have the current through every piece and the resistance of every piece, we don't necessarily need to know the potential difference because we could find it real quick. But anyways, there were two rules that we needed to solve out all of these things, right? We call these Kirchhoff's laws, and the first one was actually just current conservation, right? Electrons in has to equal electrons out. That's it. The second one was a little bit more complicated, and so that's why this one gets its own slide again. But this is what we call the loop law. Here's the idea. If I start at one particular point, I wanted to emphasize that a little bit more. If I started at one particular point and I follow a path around my circuit, so if I go through this first piece and through this second piece and through this third piece and through this fourth piece, and notice the direction of the loop does matter here. But from my starting point, I look at the potential difference from component 1, from component 2, from component 3, from component 4, and then I'm back to my starting point. And we had this very important piece of information that potential is path independent. That means if I started at 5 volts and I took some long path around and I came back to my starting position, I should have 5 volts again. It shouldn't have changed. So every potential difference that we experience should sum up to be 0 at the end. This is really saying that delta V total is equal to 0. Every single piece sums up together to be equal to 0. Between these two, the loop law and the conservation of current, that's all we need right now to solve out any circuit that gets thrown our way. So that's great, but how do these pieces actually contribute to a change of potential? Well, we're only going to look at two pieces for now. Being batteries and resistors. So batteries are the easier one to deal with. The idea here is that they are going to provide some sort of potential difference, and it just depends on how the battery is oriented. So, for example, if we had V is equal to 0 down here, towards the more negative side of the battery, then on the other side of the battery, up here, V would be equal to a positive curly E. And if we're following a loop, if we're taking that path, we went from 0 up to curly E, so that change of potential would be a positive E. If we go the opposite direction, what I would call against the battery, right? On the left-hand side here, we have with the battery, we have against the battery on the other side. Same kind of deal. Let's imagine that I started at V is equal to 0 right here. I was on the more positive side, then on the more negative side, I would have V is equal to negative E. So our change of potential, according to that path, is negative E. Now keep in mind, through all these problems, I don't actually know what the potential is. V could be 0, it could be 100, it could be 200, I don't know. And it doesn't actually matter. Because really, every single time we look at these equations, every single time we're dealing with a delta V, and I keep harping on this delta V. The delta V is the important one. What the potential actually is not really important to us right now. So delta V is the thing that we're actually going to care about here. Now, that's one piece, and I always think about the battery as supplying a bunch of potential and the resistors spending that potential. So if we were to go along the direction of the current in our loop, right? If our loop drawn in blue here goes along with the current through a resistor, that resistor is spending the potential difference. It's a negative IR. And then if we reverse the direction, we reverse the sign, so it ends up being a positive instead. Negative of a negative is all that really is. So with those pieces, batteries and resistors, we have everything that we need to worry about as far as changing the potential in a circuit. Now, I kind of hinted at this last time that there are other things that we might do. We might have more than one resistor. And in fact, we've seen one problem where we had two resistors. And I mentioned that there was a shortcut to solving that problem, and today's the day we actually look at that. If we were to put a bunch of resistors in series, so sequentially one after the other, all along one wire, one path, then what we would find is that we could equivalently say that we have one resistance because of all of those resistors, the equivalent resistance, and that equivalent resistance would be equal to the sum of each resistor. The idea here is that sometimes, so let's talk about a practical place that this might show up. Anybody who has built any sort of electronics might know that there are not every single value of resistor. Not commonly, at least. Like, I'm sure you could get some, but like, most of the time they come in like 3 or 4 values per magnitude, right? I think a lot of people often see there's the 10, there's the 22, there's the 47, and that's typically the values that we see for these things. They're just common values for some reason. I don't know the history on that one. But what if we needed 80 ohms? And we've got 22 and 47 and 10. Well, for one, we can get very close to 80, and typically that's good enough. But the idea here is that we don't always have these values that we're looking for, so it's practical to be able to use this to say, I need this resistance, I need some combination of resistors that's going to get me this resistance. And then thinking back to what we were talking about, the definition of resistance, this is my example of more obstacles in the path means it's a harder time for the current to get through, right? But luckily, it's the same current throughout all of these because current in equals current out, equals current in, equals current out, every single one of these. But I could rewrite this as just one single resistor with quantity capital R. So this is the easy one. The other side, remember we've got series and parallel. Parallel is when you have different resistors along individual paths. And this one's a little bit more difficult to deal with. For one, because imagine this for a minute. If I am looking at these 3 paths, current is not the same through these. Not necessarily, at least, right? For this top path, I might have a current I1. Then I might have another path, I2, and another path, I3. These might be equal, they might be different, I don't know. It depends on the resistor. What we do know is that the current coming in gets split up between each path. So I1 plus I2 plus I3 is equal to the total I coming in is equal to the total I coming out. But while we are in these split paths, the current is going to split up. However, they all do have the same change in potential, which is nice, right? So over this entire thing, whether it's 3 resistors or 1 resistor or 2 resistor, however many paths it branches into, the potential difference over that is going to be equal. The math to do this is a little bit more complicated. It's what we call reciprocal sum. So it's a little bit messy, right? You've got to do some inversions and some fractions and all that good stuff. So series is much nicer to deal with, but yeah, we can't win all of them. So let's try this out. I have a diagram right here that's got 5 resistors in total, and what I'm interested in finding is the equivalent resistance. What is the true resistance between A and B? Not every single one of these quantities, but what's the full resistance? If I looked at just input, output, what's the resistance between those 2 points? Now, before you get started, I've got one last thing that we need to look at here, and one more thing that we need to think about. When we're looking at this diagram right here, there is 1 resistor per path, and that's important. In this diagram right here, I can't just say R1, R2, R3, R4. It doesn't work like that. When we're looking at the parallel resistors, what we're really looking at is the resistance per path. The resistance per path is the most important thing. So you can't just dive into the parallel resistors equation. You're going to have to start somewhere else. You're looking for 3 steps, at least in my mind, 3 steps to solve this one out, not just 2. All right, so let's go ahead and take a look at this one. So, and I'm going to draw plenty of pictures on this thing, which is, this will become kind of a more customary thing. So, as I said before, we can't just immediately jump into parallel because we need to know what the resistance along each path is, right? So we've got 2 splitting paths. I need to find the resistance along each path. That means I need to actually start with resistors in series. So along the red path, let me move this thing over just a little bit. Got a little bit more room to write on this side. Along the red path, this one right here, I'm going to say the resistance, because it's in series, is 10 ohms plus 40 ohms. Nice and easy, doesn't require any sort of fractions or anything else, for a total of 50 ohms. Along blue path, resistance is going to be 55 plus 20. Total of 75 ohms. Now, I'm going to go ahead and actually redraw this thing, because that's one step that we should get very comfortable doing, because we're going to have to do a lot of redrawing, a lot of drawing out these diagrams in multiple different ways, because it's so much easier this way. I promise, I promise, I promise. I used to do these things on the second floor of Best. I would take up like an entire whiteboard to draw out all the different variations of the circuit that I could have, right? Every single step, I was collapsing these resistors into equivalent resistors. And I would sometimes fill up an entire board, but it's what I absolutely recommend. I know it takes up a lot of space, but I still recommend it anyways, because as we get into some of these problems, we're going to have a lot of different things to keep track of, and the easiest way to keep track of it is if you have pictures for every step. So I'm going to go ahead and do that here. So we didn't do anything to this 10 at the bottom, but we still have our point A, our point B. We've still got our 10 ohm resistor. But now, on each side, we've got 50 and 75. So now, I can't combine anything in series yet because I have these branching paths. What I'm going to have to do is collapse these 2 that are in parallel. So I'm going to say these 2 right here, parallel Rs. Parallel resistors. So the way to do that is that the equivalent resistance is equal to 1 over 50 plus 1 over 75. And we're about to see something that's really interesting. When I solve this thing out, and I'm going to go ahead and combine these fractions, find the lowest common denominator. So this is 3 over 150 plus 2 over 150, 5 over 150, which means that our resistance is 150 over 5 is only 30 ohms. Lower than the other 2. So part of the analogy that I made when I was talking about resistance is that more lanes gives us more pass-through area, essentially, right? I can increase the current going through some sort of resistor if I have a bunch of different lanes. If there's more obstacles in the way, it's harder. But if I have more lanes, everything's going to move a little bit faster. And that holds true here. And this is a really interesting thing, because what you can even do is if I have a 100 ohm resistor and a 100 million ohm resistor, the total resistance is still going to be smaller than 100 ohms. I like to think of it like this. If I've got a highway and I've got like a real rough back roadway trying to move between 2 cities, there's always that one suburban dad that's like, I know the way there. And he doesn't take the highway, and he adds 2 hours to the trip. You don't know why he does it, but one person does. One person goes through that path. And even if it's not a big difference, that one person getting off the highway makes it just a little bit easier for everyone else on the highway to travel. The current increases anytime I add any additional path, whether or not it's an easy path to take. If it's a 1,000,000 ohm resistor, if it's a 1,000,000,000 ohm resistor, it doesn't matter what I'm adding. If it's in parallel, it's going to make the path through for every path a little bit easier. So always expect to see that. If you have resistors in parallel, the value you should get should be lower than any other value that you saw going into it. But that is our 30 ohm resistor. So I'll take one more step and I'm going to say, okay, let's reduce this by one more. Now, point A down to one resistor, down to a second resistor, down to B. So this was 30 ohms. This was 10 ohms for a total resistance. Oh, I wanted that in orange, please. For a total resistance of 40 ohms. And that's it. That's the equivalent resistance. This entire thing simplifies down to one resistor with 40 ohms of resistance. Now, if I was asked to find the current going through each resistor, then I would start working backwards. And that's why I kept all of my pictures. Because I would have to think, okay, well, what's the current going through this piece right now? And then I'm going to have to split that up into each path. And then I'm going to have to split that up again when I, uncombine those resistors. So that's why I like to keep all of my pictures together, and I like to draw this kind of sequence as I reduce down, labeling everything, making sure that all my pictures look pretty good. So, a concept check. And this one is a little bit divisive. There's a few ways that I can describe this one and talk about it. But let's imagine for a minute here. I've got this sort of circuit, and it begins open. So the switch is open. There's no current passing through the middle, just like it's drawn here. Both light bulbs are glowing. Then I close the switch, so that becomes a consistent path all the way through. What happens to each light bulb? All right, so this is kind of an interesting one. And despite the fact that it's conceptual, to really prove my points, I might have to go into some equations here. A is going to get brighter. A is certainly going to get brighter. But let's talk about why. At a bare minimum, whether in reality or in this ideal world where wires have zero resistance, A is going to get brighter because if I'm looking at my loop, current comes from the battery. It gets split up between these two paths now. I'm splitting up these two paths. The resistance that I had was something, right? It was whatever the resistance from this light bulb was. But by adding a second path, whether or not there's another resistor there, the total resistance has gone down. The total resistance of this circuit has gone down, and that means that the current is going to go up. The same potential difference from this battery still needs to be dissipated. So if I'm looking at the total resistance, so this is from the battery versus the resistance of the total circuit. The total resistance has gone down, but the voltage from the battery is still the same. And that means the current has to go up to compensate. Power, I squared times R. Power goes up, brightness goes up. A certainly gets brighter. Now what happens to B? That's a bit of a different story. We need to really think about what happens when this current gets split up. See, we run into this little bit of an issue where even though at a certain point, let's imagine now we have gotten to an extreme where we have the hyper highway and the dirt road through rainforest jungle. At a certain point, not even that confident, maybe falsely confident suburban dad is going to try and take that path. This is what I would call a short. When you're talking about something being short-circuited, this is what's happening. You have a sudden path that has no resistance, or very nearly zero resistance. And suddenly, all of the current that we had is being diverted down this new path. Now, in reality, because wires still technically have a little bit of resistance, there is a little bit of current going through our original path through light bulb B, but it's that much. It's a tiny, 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 tiny little bit of current, to the point that you would not be able to tell that this light bulb had any current going through it whatsoever. Whereas my short has nearly the full current. If I assume that it's ideal wires, what I'm looking at here is there anything along this path to use up any potential difference? There's no resistance. That means that if I were to draw, let me change color real quick. If I were to draw this loop, this implies that resistor A is taking up all of the current. The second path, a second loop, if I drew a loop right here, I have 0 is equal to IRB. There's no current. If there's a tiny bit of resistance, if the wires are realistic and have a little bit of resistance to them, then there will be a little bit of current. But in our ideal scenario where there's not really any appreciable resistance to these wires, there's no current that goes through B. So what I can say, let's compromise just a little bit here. B nearly goes out. It's going to be so dim that you can't perceive it. It's not going to glow. It's not going to do anything like that, right? There are maybe a handful of electrons going through it, but not any more than that. But A would certainly get much brighter. Okay, so I'd like to take a look at one more whiteboard problem for the day here. We've got a little bit of a simpler circuit, although we don't know what's on the outsides here, right? We just know that current comes in, splits into two paths, goes R1, R2, and then recombines. How much current is going through R1, and express that exclusively using I, R1, and R2? It's going to appear you need to use both of Kirchhoff's laws. I will tell you that. You need both laws. You need two equations here to make this work. But go ahead and get started on that one. All right. How's about we start to take a look at this? So I'm not going to need to draw pictures, multiple pictures at least, for this one, right? I'm just going to go ahead and copy the picture I've got already. But I'm not going to need to collapse this down like I might some of the other problems. There's nothing crazy going on here. We've got two resistors, and if there was other knowledge about this, if I had a battery over to the side or something, I might have to redraw this in some way or another. But since we're really not concerned about what's going on outside of there, I'm not going to worry about it either. So first things first, conservation of current tells me that the current coming in, capital I, splits into I1 plus I2. Right, and I know that I've got to deal with this because I've got a junction. If I've got a junction, if I've got current splitting out, I need to use a conservation of current equation. I could also think of this as I1 plus I2, leaving capital I. Now, let's take a step back real quick, because I kind of jumped the gun here. Let me say, okay, we're given our variables that we're interested in using here are I, R1, R2, and we need to find I1, which means that we're most of the way there in our brand new equation, but we can't use I2, so we need to come up with something else for that. Okay, well, I can't do current conservation again because I've already done it, right? But what we can do is come up with a loop equation here. Pick an arbitrary direction, doesn't really matter which one. I'm going to say, let me start right there in that corner, and I'm going to take a counterclockwise loop like that. So, first one, we already know right off the bat, delta V is equal to 0, right? No change of potential if I come back to my initial position. Then I go with the current through R1, so that's a negative I1 R1. And then I go against the current through R2, so that's a negative positive I2 R2. Okay? And if I look at this thing, I can say, okay, I1, I like that. R1, I'm fine with that. R2, I'm fine with that. And it's got I2 in it. We can rearrange this in terms of I2 and plug it into our equation in orange. So let's do that. I'm going to move over one of these terms first. And this step right here, there was actually another way that we could have gotten here. We could have also said in just the same way that the potential difference between 2 points is the same. So the potential difference I1R1 should match the potential difference I2R2. That was another equivalent way to write this out. That would have been fine just as well. But I went with a loop equation instead because it's a little bit more consistent. We'll use that a lot more. But that was another way we could have done this, or could have conceptualized this to begin with. Now, again, I said I'm rearranging this in terms of I2. And this becomes a ratio of the two resistors. And this is another cool thing, right? This kind of re-exemplifies what we are talking about with the current splitting up between different paths it has. If R2 is huge, if R2 is a billion and R1 is 1, then we expect to see that I2 is a billionth of I1. Most of the current goes through I1 and a tiny bit would go through R2, right? There's always that one that decides to take the hard path, but most of them are going to go through the easy path, the path of least resistance. But it does split up. The total resistance would go down because of that. So let's take this and let's plug these two in together. Something like that. And now we're going to say that I is equal to I1 plus my replacement for I2. Pull out the I1. Divide over these other constants. And I love this equation right here because this is going to tell us the exact same thing again. This is telling us that we have, if the current I comes in, all of it goes into I1 minus whatever that ratio is. And it's not quite a minus, but, you know, kind of taken away from that, right? The larger this ratio is, or the more equivalent these two resistors might be, the more evenly split we're going to see this current, right? If R1 is 100 and R2 is 100, then we're going to see 100 over 100 is another 1, so it would split evenly. The current going through I1 would be I over 2. If we go the other way, if R1 is much, much larger than R2, then this becomes minimally small, right? We look at the very, very, very tiny I1, and that implies that the rest of it would be going into I2. So we can kind of pick apart this equation and get these same ideas back about what happens when you're talking about parallel resistors like this. But this should be our final expression that we see for that current. Because remember, it's based on the direction that I go. So if I go with the current, so if I'm looking at like this picture, for example, if I'm going with the current, that's a minus IR, whereas if I'm going against the current, that's a plus IR. That's where that one's coming from. I talk about that a little bit in the 28-1 lecture. The easiest way to think about it is what happens when you're drawing a loop with one battery and one resistor. Like if I were to draw, I can draw this one out real quick. Say I've got a battery. Oh, that was not very straight across, was it? And one resistor. So here's the positive end of my battery, here's the negative end of my battery. So if I were to pick a starting point right here, and I draw my loop going around. The current would be going like this, from the positive end of the battery through the rest of the circuit into the negative end. So what I would expect to see then is delta V is equal to 0, and I'll call this potential curly E. Positive curly E minus IR gets me back to 0, right? The battery provided a big potential difference, the resistor spent all of that potential difference, and we're back to our starting point with no change of potential. If I were to reverse the loop, if I took this loop instead, now my battery would be negative because I'm going against the battery at this point, but to get back to 0, I've got to make IR positive. If we reverse that direction, if we go against the current, then we're taking just the negative of a negative value. Does that make sense? I'm going to say let's call it there for the day. And the reason I'm calling it quite a bit early is because we do have a lab and it's a little bit more intensive. It's a little bit longer than the other ones that we normally do. It's worth more points. But it goes through and it works a lot with this in a practical application, right? You get to design your own circuits and build those things and mess around with it, and you can do all sorts of really fun things with that simulation. It's a really well put together simulation, so you know, I try to have a lot of guided questions, but then have some fun, experiment a little bit with it. It's an easy way to figure out what would blow up components without actually blowing up components. So we'll call it there for right now, right? And then the lab will fill in some of these other details. We'll come back next time around with 28-3 and start to look at how we can analyze more and more complicated circuits as we go along. But that'll be it for now. So I'll see everyone again next time.